So we've already talked about differentiation in year one. We talked about how to differentiate terms of the form x to the power of n. To start this chapter, we're going to introduce some new derivatives that you need to know that are of functions that you've seen before. So if y is equal to sin of x, then dy over dx, we talked about this terminology in year one, this means we're differentiating y. Dy over dx is equal to cos of x, and along the same lines, if y is equal to sin of kx, where k is any number, so k is equal to 2, 3, 4, something like that, then dy over dx is equal to k cos of kx. So this k here comes to the front and becomes a coefficient. And if y is equal to cos of x, then dy over dx is equal to minus sin of x. And along the same lines, if y is equal to cos of kx, then dy over dx is equal to minus k sin of kx. So if you have a number here, then it basically becomes the coefficient here. Just a quick note, when we're differentiating trig values like sin and cos, we have to use units of radians when we're plugging values into the derivatives here. We never use degrees. So here's some examples. So if y is equal to sin of 2x, therefore dy over dx is equal to, so we're going to use this down here with k being equal to 2. So dy over dx is equal to k cos of kx, therefore dy over dx is equal to 2 cos of 2x. The key is when you're differentiating trig functions is swapping out the sin for the cos, or if it's the cos, swapping out the cos for the minus sin. And whatever this number is here, when you differentiate it, it comes out and to the front when you differentiate it, and it becomes the coefficient. Just another note that some people make a mistake with is this here is still 2x. A lot of people make that mistake and just write it as x. This here is still 2x like it is up here inside the function. Okay, let's say that y is equal to cos of 3x, therefore we're going to use this here with k being equal to 3. So we differentiate the cos and it becomes minus sin, and then the 3 is going to come to the front, so therefore y is equal to cos of 3x, dy over dx is going to be minus 3, the 3 comes to the front, and it's the minus 3 sin of 3x, like this here. Okay, let's say that y is equal to 3 sin of 5x. Now, we talked about this in the year 1 differentiation video. When we have the coefficient here at the front, this doesn't have an effect. All that we just do is multiply what we differentiate by 3 as well. So remember, this is actually 3 times sin of 5x. So dy over dx is also 3 times, and then we individually differentiate this and separate this. So you differentiate this and then just multiply it by the coefficient at the end. So therefore it's going to be 3 times, and then sin of 5x differentiated is going to be, so it's going to be the 5 and then cos of 5x, and then we can simplify this because 3 times 5 is equal to 15. So it's going to be 15 cos of 5x like this here. And then for this one here, we talked about this again in year 1. When you have multiple terms, all you do is you just individually differentiate the terms. So let's start with this one here. So we've got this 2 at the front, so it's going to be 2 multiplied, and then we individually differentiate this here. So it's sin half x, so this half is going to come to the front, so it's going to be half cos of half x, and then this is minus 12 multiplied, and then cos of 4x differentiated is going to be minus, because cos is minus sin when you differentiate it, minus 4 sin of 4x like this here. And then we can simplify this. 2 times a half is just equal to 1, so it's cos of half x, and then this is going to be minus 12 times minus 4 is plus 48, and then it's sin of 4x. So dy over dx is equal to cos of half x plus 48 sin of 4x. Now, the specification says that you need to know how to prove these derivatives, and we prove the derivatives in the same way that we did in year 1, using first principles and the formula for first principles. Now, we did an entire video dedicated to this in year 1, so go back to that if you need a reminder. In that video, we explained how first principles actually works and where the formula comes from. So the formula is given here. This is given to you in the formula booklet, so you have access to it in the exam. And we're told that f dash of x, so this is the derivative of of f of x, and as we're trying to prove the derivative of sin of x, therefore in this example f of x is equal to sin of x. So f dash of x is equal to the limit as h approaches 0, and what this means is that h is not equal to 0, but it's very, very close to 0, and it's a very, very small number. So the limit as h approaches 0 of f of x plus h minus f of x, and this is over h, like this here. And we need to rewrite this not in terms of f of x, but in terms of sin of x here. So therefore we're going to replace this f of x with sin of x, and this f of x plus h, when we have f of x plus h, what this means is we replace all of the x values with x plus h, so therefore it's not going to be sin of x, we're going to replace this x with x plus h, so it's sin of x plus h. So therefore we can rewrite this in terms of sin of x like this here. We still need to, for all of our working, we need to write this limit as h approaches 0 for all of the lines. So we've replaced the f of x plus h with this, and now it's minus sin of x over h like this here. Okay, so with this, we can use the addition formula on this sin of x plus h. Remember, the addition formula we talked about in chapter 7 is sin of a plus b is equal to sin a cos b plus cos a sin b, with x being equal to a and h being equal to b. So therefore we can write this as sin a, so it's going to be sin x, and then cos b, so it's going to be cos h, plus cos a, so it's going to be cos x, and then sin b, so it's going to be sin h, and then it's still going to be minus sin x over h, like this here. I'm just going to slightly rewrite the top here. I'm just going to rearrange the order. So now I've grouped the sin x terms together like this here, and I've got the cos x term like this. And what I'm going to do here is I'm going to factorize out for these two here. I'm going to factorize out this sin x here, and we're just going to be left with, so you factorize out sin of x here, we're just going to be left with cos h here, and then if you factorize out sin x from minus sin x, it's just going to be minus 1, and all of this is still over h like this here. Remember to write for every line of working still this limit as h approaches 0. And then for this term here, I'm going to factorize out the cos x, so therefore this is now just going to be sin h, still going to be over h, so it's going to be like this here. So we've rewritten f dash of x. Okay, so we're left with this here, and I want to focus on this cos h minus 1 over h and this sin h over h here. And I want to remind you of the small angle approximations that we talked about in chapter 5, that when theta is small, sin theta is approximately equal to theta, and cos theta is approximately equal to 1 minus theta squared over 2. And we made a video on small angle approximations back in chapter 5, and we said that we can use small angle approximations under two conditions. The first one is whatever we're talking about, so theta in this case is in radians, and 2 if theta is a small number. And if we look at this h here, well, it's going to be in radians because, as we said before, we only ever differentiate in radians, we never differentiate in degrees, so h is in radians. And also this limit here is when h is approaching 0. So remember, this is when h is not equal to 0, but it's very, very close to 0. Therefore it's going to be a very small number, so therefore it satisfies both of the conditions for small angle approximations. So therefore we can use the small angle approximations for h here, for sin h and cos h. So if we sub these in, so we have this cos h here, so if we sub in 1 minus h squared over 2, like we've done here, and then this 1 will cancel out with this one here, so we're left with minus h squared over 2 over h, and then this h will cancel out with one of the h's up here, so we're left with minus h over 2. And the question is, what is minus h over 2 going to be approaching when h is approaching 0? And minus h over 2 is also going to be approaching 0 when h is approaching 0, because the only difference is that we're dividing by 2 and it's negative, but when h is approaching 0, that's not going to make a difference, it's still going to be approaching 0 like this here. So cos h minus 1 over h is approaching 0 with this limit here, so this here is also approaching 0. And then if we focus on this sin h over h here, so we sub in the sin h is approximately equal to h, like this here, and then this h is going to cancel out with this h to just leave us with 1. It's more technically appropriate because h is approaching 0 to say it's approaching 1. So sin h over h is approaching 1 under this limit here, so it's approaching 1 like this here. And what we can do next is we can get rid of this limit here and just say that this is equal to this value and this here is equal to this value here as well. So that's what I've done down here. So I've subbed in 4 cos h minus 1 over h. I've subbed in the 0 that is approaching here, and for the sin h over h I've subbed in the 1 that is approaching here. So it's going to be 0 multiplied by sin x, so this is going to cancel out, and then it's going to be 1 times cos of x, which is cos of x. So therefore f dash of x is equal to cos of x. We've proved from first principles that the derivative of sin x is cos of x, and we've done that using small angle approximations. And then for the proof from first principles that the derivative of cos of x is minus sin of x is basically the exact same. You write it in this form and then you use the addition formula for cos of a plus b to write it in this formula here, and then you factorize out the cos of x and sin of x and use the exact same things here using the small angle approximations, and you get that it's minus sin of x here. Now, you also need to know the derivatives of exponentials and the natural log, which I've shown here. So if y is equal to e to the power of x, then dy over dx is also equal to e to the power of x. And if y is equal to e to the power of kx, where k is just any number, so 2, 3, 4, something like that, then dy over dx is equal to ke to the power of kx. We already talked about the derivatives of these exponential functions in the year 1 video on exponentials in year 1 chapter 14. And then if y is equal to the natural log of x, then dy over dx is equal to 1 over x. Now, the exponential and the natural log derivatives come up a lot, and you really need to remember them. And they come up all the time, and they also come up in the integration chapter as well. So you really need to get a basic understanding and really remember these exponential and natural log derivatives. This one here doesn't come up as much, but the specification specifically talks about the fact that you need to know and understand it. What it is that if y is equal to a to the power of kx, where a and k are random numbers, then dy over dx is equal to a to the power of kx, so this bit here is the same, multiplied by k, the natural log of a. It looks quite confusing with all the letters, so I'm just going to show you some examples of how it works. So let's say that y is equal to 2 to the power of x. So in this instance, a is 2 and k is 1. Remember, there is actually a 1 here, but we don't write it. So k is equal to 1. So therefore, dy over dx is equal to, so this part here is the same. It's still going to be 2 to the power of x, but it's multiplied by k times the natural log of a. So k is 1, so we don't write this bit. So it's multiplied by the natural log of a. So it's the natural log of 2 in this instance. Let's say that y is equal to 3 to the power of 4x. So in this instance, 3 is the a and 4 is the k. So therefore, dy over dx is, so again, this part here is still the same. It's 3 to the power of 4x, but it's multiplied by k times the natural log of a. So this is going to be 4 times the natural log of 3, like this here. So that's how it works. I just want to make a quick note for the natural log of x. You might be wondering what the derivative is of the natural log of k of x. So for example, what's the derivative of y is equal to the natural log of 2 of x? Well, this natural log of 2 of x, we can rewrite this as the natural log of 2 plus the natural log of x, like this. If you remember your laws of logarithms back in chapter 14 of year 1, if you have a natural log of something plus the natural log of something else, you can combine them into one log by multiplying them together. So 2 times x is equal to 2 of x. And then if we differentiate this here, this natural log of 2 is just a number, it's just a constant, so therefore when you differentiate this, this is just going to go away. So this is going to go away, and then the derivative of the natural log of x is just 1 over x. So the derivative of the natural log of 2x is just 1 over x. So therefore the derivative of the natural log of kx is just 1 over x. This k actually has no effect. It's still just 1 over x. Okay, so let's do some examples. So let's say that y is equal to e to the power of 4x. So this is in this form here where k is equal to 4. And the derivative of e to the power of kx is really easy. The only effect is that when you differentiate it, this k comes down as the coefficient here and everything else is the same. So the derivative of e to the power of 4x dy over dx, this 4 just comes down, so it becomes 4e to the power of 4x, and then that's the only effect. Okay, let's say that y is equal to 2e to the power of minus 2x. Remember, we have this coefficient here, so when we do dy over dx, we're going to go 2 times, and then we just differentiate this e to the power of minus 2x, which is going to be minus 2 e to the power of minus 2 of x. So this minus 2 just comes down here, and then we can simplify this by multiplying the 2 coefficients by the minus 2, so it becomes minus 4 e to the power of minus 2 x here. If y is equal to a half e to the power of 4x minus the natural log of x, dy over dx is going to be, so this half coefficient is here, and this is multiplied by the derivative of e to the power of 4x, which is 4e to the power of 4x like this, and then this is minus the derivative of the natural log of x, which is just 1 over x. And then we can simplify this. Half times 4 is equal to 2, so it's 2e to the power of 4x minus 1 over x. So for y is equal to the natural log of x squared, you might be looking at this initially and not knowing how to do it, but the key to this is remembering the laws of logarithms and remembering that when you have something to the power like this here, you can rewrite this by putting this at the front as a coefficient, so it becomes 2 natural log of x like this, and this here we can differentiate. This is going to be, so we have this coefficient here 2 multiplied by, and then we differentiate the natural log of x, which is 1 over x like this, which we can write as 2 over x. So dy over dx is equal to 2 over x. And then for the fifth example, again, we can't differentiate this directly, so what we have to do is we have to simplify it first, like the previous example. So we have 1 plus 2e to the power of x over e to the power of 3x. What we can do is we can separate this numerator, so it becomes 1 over e to the power of 3x plus 2e to the power of x over e to the power of 3x. And what's good about this is we can simplify this here as e to the power of minus 3x, and this is plus 2, and then it's e to the power of x over e to the power of 3x, which is going to be e to the power of x minus 3x, which is e to the power of minus 2x, and this here we can differentiate directly. So e to the power of minus 3x is just going to simply be minus 3e to the power of minus 3x, and this is going to be plus 2 multiplied by, and then this differentiated is going to be minus 2e to the power of minus 2x. This is e to the power of minus 2x differentiated, and then we can simplify this to minus 3 e to the power of minus 3x, and then 2 multiplied by minus 2 is minus 4 e to the power of minus 2x, like this here. Now, for this final example, I just want to go through a really useful tip, in my opinion, that I don't think enough people know about in order to check your answers for differentiation questions. I also talked about this in the year 1 video on differentiation, but I'll go through it quickly here as well. Your calculator is actually able to do differentiation questions. So on your calculator, if you press shift and then this integration symbol here, it gives you this thing here on your calculator, and in this box here, you can put in the expression that you're trying to differentiate. So in this example, we're differentiating this expression here. So put this expression into your calculator. You can put x in by using this x symbol here, and then you can see that we have this little x equal symbol here. If you put a value into this, so let's say 5 for example, and then you press equals, your calculator gives out a value of minus 1.825 times 10 to the power of minus 4. What this value is your calculator differentiating this expression here and then subbing in the value of x. So x is equal to 5 in the example that we did. So why is this useful to us? Because what we can do is we can sub in the same value of x into our derivative that we figured out in the question. So we used 5 in that particular example. So sub 5 is equal to x into this derivative here. So it's going to be minus 3e to the power of minus 3 5 minus 4e to the power of minus 2 5. And if you put this here into your calculator, it also gives out a value of minus 1.825 times 10 to the power of minus 4. So in the first step, our calculator has differentiated this expression here on its own and then subbed in the value of x is equal to 5 and got out the value of minus 1.825 times 10 to the minus 4. And in the second step, we have used a derivative that we figured out ourselves previously and also subbed in the value of x is equal to 5 manually, and we have also got out the value of minus 1.825 times 10 to the minus 4. And because these two values are the same, this tells us that this answer here is correct. We've got the answer right, we've done all of our working out correctly, and we can move on to the next question knowing that we've got the answer right. Now obviously you can't just use this to solve the question, this method. One, because it doesn't work like that in this particular example. Your calculator can't actually give out this expression here. In some particular questions that we'll see in this chapter, the way the question is worded, you could actually just use this calculator method in order to get out the particular answer. And if that is the case, you obviously cannot just use this method in order to get out the final answer and just write out the number that's required, because obviously the examiners are aware that this function exists on your calculator, and if you just write this number out without any working out, you'll get 0 marks. The examiners will know you haven't actually done anything, so please don't do that. What this method is good for is checking your final answer to see if you've got it right. Use this trick, and if you get the same values, you know that you have got the answer right and you can move on to the next question confidently knowing that you've got all the marks. If you figure this out and you have got two different values out, you know that you have done something wrong in your working and this is not the correct answer. You need to go through your working and check where you've made the error. I think this is a really good way to check if you've got the final answer and if you've done all your working out correctly. Now, really quick, the book does the proof of this derivative here, that if y is equal to a to the power of x, prove that dy over dx is equal to a to the power of x multiplied by the natural log of a. Just because the book does it, it makes me think that you probably need to know, and it's a bit hard to figure it out on your own. There's a specific method to do it, so I'm just going to go over it really quick. So y is equal to a to the power of x, where a is just any number. So this is something like 2 to the power of x or 3 to the power of x, something like this here. So what we're going to do, we're going to rewrite this here as e to the power of the natural log of a to the power of x. We talked about this in the chapter 14 video in year 1 on laws of logarithms. If you have e to the power of the natural log of something, so for example e to the power of the natural log of b, this natural log and this e kind of cancel down and it just leaves us with this b here. So therefore we can write a to the power of x as e to the power of the natural log of a to the power of x. This is the same thing. And this natural log of a to the power of x, again remember the laws of logarithms, this x can come down like this here, so it's x times the natural log of a, so we can rewrite it as this here. And I'm just going to rewrite it the other way around. I'm going to write the natural log of a first, multiplied by x here. And this here is actually of the form y is equal to e to the power of kx, with k being equal to the natural log of a. Remember that a is just a number, so the natural log of a is something like the natural log of 2 or the natural log of 3. This is just a constant, this is just a number, so therefore this is just k here. And dy over dx is equal to k e to the power of kx, so therefore dy over dx of this here, this natural log of a comes down, so it's the natural log of a multiplied by e to the power of the natural log of a times x, like this here. And because we said that we can write this here as a to the power of x, that's what we were showing before, therefore we can rewrite this as the natural log of a multiplied by a to the power of x, and therefore we've proven that dy over dx is the natural log of a times a to the power of x, which is what's required. So here's just an example that I made of a typical exam question that they could ask you, where they want you to find the equation of the tangent to the curve y is equal to 3 sin of 2x minus cos of x at the point pi 1. Now, I talked about tangents in the year 1 differentiation video titled Tangents, Normals and Increasing and Decreasing Functions. So go back to that video if you need a reminder. But in order to find the equation of the tangent, we need to know the gradient of the tangent. We can do this because the gradient of the tangent is the same as the gradient at this point on the curve. To find the gradient at this point on the curve, we need to differentiate this, find dy over dx, and then we can find the gradient at this point. So we need to differentiate this. So this is going to be dy over dx is equal to, and we differentiate this and we do it each term individually. So 3 sin of 2x is going to be 3 multiplied by sin 2x differentiated, remember to bring the 2 at the front, is 2 cos of 2x minus, and then cos x differentiated is minus sin x, like this here, and then we can simplify this. 3 times 2 is 6 cos of 2x, and then these two minuses cancel out to give plus sin x, like this here. So dy over dx is equal to 6 cos of 2x plus sin of x, and we need to know the gradient at the point pi 1, and we can do this because we know the x coordinate is pi, so we can sub in x for pi. So this is going to be 6 cos of 2 pi plus sin of pi, and if you put this into a calculator or figure it out, remember that when you're plugging values into dy over dx, you have to use radians. You can't use degrees, you have to use radians. So use radians for this, and if you plug this into your calculator or just figure it out, this is equal to 6. So therefore the gradient at this point is 6, and therefore the gradient of the tangent is also 6. So in order to find the equation of the tangent, we need to use the formula for the equation of a straight line. Now go back to the equation of a straight line video in year 1 chapter 5, where we talk about how this formula works. But basically, in order to use this, we need the gradient of the straight line, which we figured out is 6. This is the gradient of the tangent, and we need one point that lies on the tangent, and we know this because we're told the tangent to the curve is at the point pi 1, so therefore the tangent passes through this point pi 1, so therefore this is a coordinate on the tangent, so we can use this point. So if we sub the values in, it's going to be y minus y1, so this is the y coordinate of the point that the tangent passes through, which is 1, so it's y minus 1 is equal to m, which is the gradient of the tangent, which is 6, and then x minus x1, so this is the x coordinate of the point, which is pi, like this here. We need it in the form y is equal to mx plus c, so we're going to expand this bracket here, so it becomes 6x minus 6 pi, and then we're going to move this 1 onto the other side to make y the subject, so it's y is equal to 6x minus 6 pi plus 1, and this is of the form y is equal to mx plus c. This is the equation of the tangent. So here's a couple of exam questions for you to have a go at. The first one is one that I made, and the second one is from an actual past paper. So pause the video, have a go, and I'll go through the answers in about 5 seconds. So for question 1, we're told about this curve here, and we need to find the coordinates of the stationary point on the curve. Now we talked about this in year 1 in the second order derivatives video. A stationary point exists when dy over dx is equal to 0. So we need to find dy over dx and then equal it to 0 and find the x values for which dy over dx is equal to 0. So dy over dx is equal to, so we differentiate this here, so we differentiate it term by term, so it's going to be 2 multiplied, and then e to the power of 2x differentiated is 2e to the power of 2x, and then this is minus 3 multiplied by, and then e to the power of x differentiated is e to the power of x still, and then we can just simplify this. 2 times 2 is 4, e to the power of 2x, and then this is minus 3e to the power of x. So this is dy over dx, and we need to find the values when dy over dx is equal to 0, so we need to find the values when 4e to the power of 2x minus 3e to the power of x is equal to 0. Okay, we can see that e to the power of x is common in both of these terms, so we can factorize this out, so it becomes e to the power of x multiplied by 4e to the power of x minus 3 is equal to 0, and as e to the power of x cannot be equal to 0, there is no value of x for which e to the power of x can be equal to 0. We can therefore divide both sides by e to the power of x, so it becomes 4e to the power of x minus 3 is equal to 0, and then we just solve this for x. So we move the 3 onto the other side, so it becomes 4e to the power of x is equal to 3, and then divide both sides by 4 to get the e to the power of x is equal to 3 over 4, and therefore x is equal to the natural log of 3 over 4. So x is equal to the natural log of 3 over 4. This is the only solution for this equation here when it's equal to 0. So there's only one stationary point, which makes sense because it says find the coordinates of the stationary point. There's no s here, it's just singular, so therefore this tells us that we're only looking for one stationary point. So this is the x value, so in order to find the y value we just sub x into this equation here in order to get out the y value. So this is going to be 2e to the power of 2 natural log of 3 over 4 minus 3e to the power of the natural log of 3 over 4, and if you put this into your calculator, just figure it out, it's equal to minus 9 over 8. So y is equal to minus 9 over 8. So the coordinate is the natural log of 3 over 4, which is the x coordinate, and the y coordinate is minus 9 over 8. And this is the stationary point of this curve here. So for question 2 part A, we're given two functions here, f of x and g of x, and we need to prove that the composite function gf can be written as this here. Now a lot of people don't really like this notation here. Just this here is just f of x, this here is just g of x, and this here is just the composite function gf of x, and you can write it like this if you prefer to write it in this way. Now this is a composite function question, so this is year 2 chapter 2 material, so go back to the composite and inverse functions video if you need a reminder of this. We need to find g of f of x. Now a reminder, when we're trying to find g of f of x, this is the function g of x, but all of the x values are replaced by f of x. So gf of x is going to be g of x, which is e to the power of 2x, but x is replaced by f of x. Rather than this being x, it's going to be this function, so 2x plus the natural log of 2, like this here, and we need to prove that this can be simplified to 4e to the power of 4x. Okay, firstly let's expand this bracket here, so it becomes e to the power of 4x plus 2 of the natural log of 2. Now I'll just remind you of the indices law, that if we have e to the power of a plus b, or just anything to the power of a plus b, this can be written as e to the power of a times e to the power of b. So therefore we can write this here as e to the power of 4x multiplied by e to the power of 2 of the natural log of 2. Okay, so let's focus on this bit here. So we have 2 natural log of 2, and I want to remind you of the logarithm law that we've already talked about in this video, that if we have b natural log of a, this can be simplified to the natural log of a to the power of b. So this here can be simplified to the natural log of 2 to the power of 2 instead of 2 natural log of 2. 2 to the power of 2 is obviously just 4, so this is now e to the power of the natural log of 4. And we've also talked about in this video already that if you have e to the power of the natural log of a, this is just equal to a. So if we have e to the power of the natural log of 4, this is just equal to 4. So now this is just e to the power of 4x times 4, which is 4e to the power of 4x, which is what's required. So gf of x is equal to 4e to the power of 4x. So for part D, I've skipped B and C because they're not really relevant. We need to find the value of x for which d over dx of g of f of x is equal to 3. So gf of x we figured out is equal to 4e to the power of 4x, and this d over dx basically just means differentiate. So what this is actually saying, d over dx of gf of x, is d over dx of 4e to the power of 4x. We need to differentiate this here and then equal this to 3 and then find the value of x, which is the case. So firstly, let's differentiate this here. So 4e to the power of 4x differentiated is going to be, so we have this 4 coefficient here, so it's going to be 4 multiplied by an e to the power of 4x differentiated. We'll bring this 4 down, it's going to be 4e to the power of 4x. So this is going to be equal to 16e to the power of 4x. And we need to find the value of x, which this is equal to 3. So we need to find the values of x, which 16e to the power of 4x is equal to 3. Divide both sides by 16 to get e to the power of 4x is equal to 3 over 16. And then 4x is equal to the natural log of 3 over 16, and divide both sides by 4 to get that x is equal to 1 over 4, the natural log of 3 over 16. So x is equal to this here, but it wants the answer to 3 significant figures, so we need to figure out what this actually is in our calculator. So x is equal to, if you put this into your calculator, minus 0.418. So to 3 significant figures, x is equal to minus 0.418.